for April Fool's Day, I brought in a comic and large pencil and I just started using it in class.
Good morning, everyone. Are we ready for some Taylor polynomials?
Yes.
Is it what you've been looking forward to all weekend? Yes. Taylor polynomials?
Absolutely.
Let's go.
I didn't think of a reasonable one.
Taylor polynomial. So when we think about these Taylor polynomials, we should be thinking generalized tangent line. So the idea is that a tangent line is the best linear approximation, and a Taylor polynomial is the best quadratic, cubic, quartic, wherever you want to stop. It's creating the best approximation possible going out to however far you choose to go out or however far we're told to go out. And so when we look at this one, we are asked for p sub 4 and p sub 5. So that's the fourth order Taylor polynomial is p sub 4. The fifth order is p sub 5. So those are out to the fifth derivative and the fourth derivative. And what we are going to see is that when we build these Taylor polynomials, this one we built at 0. This one we're going to build at pi over 6. And what we are going to see as we go through some of the stuff today is that if our center is not 0, this really is the only way to build the polynomials with this derivative process. If the center is 0, there are sometimes other ways to create your Taylor polynomial. So just keep that in mind. If the center is not 0, you should definitely just start taking derivatives and use this constructive process. So let's go ahead and take a look at this one. And once again, it's helpful to just sort of keep everything in columns. It's a lot easier if you can figure out a nice, clean process for this. And so we start with our function, and we're going to have to go all the way down to the fifth derivative. So we'll just create a column of derivatives first. Well, I guess that becomes positive again. And then the fourth derivative, we start cycling. So we're back to the original function after we take 4 derivatives. And then the fifth derivative will be negative sine x. So that's where we start. We create a column of the function and its derivatives. And then the next step is to evaluate the function and its derivatives at whatever the center is. So we want to evaluate each of these functions at pi over 6. So y of pi over 6 is cosine of pi over 6. Cosine of pi over 6 is root 3 divided by 2. So we're just going to go right down column 2, just evaluate column 1 at pi over 6. So the second one, sine of pi over 6 is 1/2, but we have a negative in front, so we get a negative 1/2. And then it just starts repeating. Y double prime of pi over 6. All right, cosine of pi over 6 again, that's root 3 over 2, so we'll end up with a negative root 3 over 2, etc. Once we have all of these values, then we can go ahead and build our polynomial. And it's totally fine when you build your polynomial to just sort of do p sub 5, expand p sub 5 out, and indicate which p sub is p sub 4, because p sub 5 is just p sub 4 plus one extra term. So if you want to save on some space and some time, you can be creative that way. So p sub 5, we start with the first constant up there. So that's, if we think back to tangent line, that's the y-intercept of the tangent line. So root 3 over 2 plus, minus 1/2 is the next constant. So the root 3 over 2 is a constant. And then the next constant gets multiplied by x minus pi over 6. So we're having this polynomial is going to be shifted pi over 6. So we're going to have, instead of powers of x, we're going to have powers of x minus pi over 6. And this power is just to the first. So that right there is p sub 1. That is the tangent line. So any questions to that stage? That's just the tangent line. Constant plus constant times x minus a. So that's p sub 1 right there. Now to get to p sub 2, we go next constant. And here is where we have to be a little bit careful. I'm going to jam it in the numerator because we're going to have to divide by a 2 factorial. And we're going to have x minus pi over 6 raised to the 2 power. So that is p sub 2. This is the best quadratic approximation.
Is it necessary to add the factorial on the 2?
Nah, you don't have to. Yeah, we just do it just to see the pattern because the pattern is going to
But after
persist.
3, you need it.
3, we definitely need it. Yeah.
Okay.
But you don't have to put it. Most books will put it on the 2 just to try to get us in the habit of thinking about it. So then the next one is plus 1/2 divided by 3 factorial x minus pi divided by 6 all cubed. So that's p sub 3. And let's move this a smidge to the left. I'm running out of space here. So let's get to p sub 4. P sub 4, we go to our next constant, root 3 over 2, divided by 4 factorial, and then x minus pi divided by 6 all raised to the 4th. So that is p sub 4. Maybe what I'll do is call this p sub 4 instead of stretching the board out far. Then I'll just say this. We can be creative in the way we do this. We can say that p sub 5 is then all of p sub 4 plus one more term, which is minus 1/2 divided by 5 factorial, bless you, x minus pi over 6 to the 5th. So we can do it that way. And it's totally fine to leave those polynomials like that. If we are going to simplify, the only simplification we might do are these coefficients. We could simplify these, but you don't have to. With Taylor polynomials, it's kind of nice to see the patterns that are there and to not necessarily obscure them by combining all the constants. But if you're going to combine anything, you could combine these, but definitely don't multiply out these x minus pi over 6 to whatever power. So those are our 2 Taylor polynomials, 4th order and 5th order. So on a test, it's totally fine not to simplify those coefficients. If you want to, it's totally fine also. It doesn't matter. It's the one time in math where you're not going to see points being taken off or not reducing or not simplifying. These with Taylor polynomials. So any question on the process? It's very algorithmic. Once you get into the groove of it, it's pretty straightforward. Repeated derivatives, all these divisions by factorials that match the powers. So there's a lot of symmetry here when you're doing them. All right. So approximations with Taylor polynomials. Approximate the given quantities using Taylor polynomials with n equals 3, aka p sub 3. So 3rd order Taylor polynomial. Compute the absolute error, assuming the exact value is given by a calculator. All right, so let's try this one. So our function is tangent. And if we want to get to p sub 3, we're going to need to go down to the 3rd derivative. Let's give ourselves a little more space. Tangent. Tangent has a derivative of, sec squared. So then when we get to y double prime, now we have to use the power rule, chain rule thing. So we're going to get 2 secant to the 1. So that's the power rule part. Bring the power down, subtract 1. So 2 secant to the 1. And then we have to multiply by the derivative of the base. The base of that exponential expression is secant. So now we multiply by the derivative of secant, which is secant times tangent. So that's going to give us a secant squared and then a tangent. And then the dreaded third derivative for this thing. We have a product up here. So we have to use the product rule. So we're going to do first function. So I'm going to treat 2 secant squared as the first function and tangent as the second function. So first function is 2 secant squared multiplied by the derivative of the second function. Derivative of tangent is secant squared. So that's going to make this 2 secant to the 4th power. So that's first derivative second. And then we take the derivative of the first multiplied by the second. The derivative of the first is going to be 4 secant to the 1. So bring down the 2, subtract 1, but then we have to multiply by the derivative of secant, which is secant tangent. So that's going to add a second secant and then a tangent. And then multiplying by the second function is going to put in a second tangent. So we'll have that. Yeah?
Could you also make tangent u equal tangent, and then du would be secant squared?
Well, we're not integrating.
Oh,
If we were integrating, yes.
cool.
Yeah, if we were integrating, that would work great. Yeah, we're not integrating here, though. So that is our first column for our Taylor polynomial. Second column, we evaluate at the center. So we have to choose a center. And so the center is going to be a number as close as possible to this value that we're approximating at that's easily evaluated in all these functions down here. So we want to pick a number that's close to that. The obvious choice is, I think I heard it, 0. So if we look at these trig functions, what are the 2 values that we can plug into tangent that surround negative 1/10? So if we have negative 1/10, certainly 0 is on the right. What is the value on the left for which we know all those trig values? We can go a lot closer to negative 0.1 than pi halves. Pi halves is 90 degrees down.
Pi fourths.
Even closer, pi over 6, right? Negative pi over 6. So the special angles that we know are multiples of pi over 6 and multiples of pi over 4. The closest of all those to negative 1/10 would be that. So that's about negative 1/2, right? Pi is about 3. 3 divided by 6 is about half. So these would be the 2 values that you could look at. 0 is closer to negative 1/10 than this is. If you plug both of these if you plug this one into your calculator and get a decimal approximation, you'll see that 0 is closer to negative 1/10 than negative pi over 6 is, because negative pi over 6 is close to 0.5. Everyone following that? So we're going to choose 0 because this is closer. So whichever one is closer, for which you can evaluate all of these exactly and easily, we'll choose that one. So we're going to choose our center to be 0. So now we're going to evaluate y of 0. Tangent of 0 is 0. Y prime of 0. Secant of 0. Secant of 0 is 1, because cosine of 0 is 1, and square it, we get 1. And then we have y double prime of 0. Y double prime of 0, this multiplication here, tangent of 0 is 0, so that's going to be 0. And then we've got our third derivative evaluated at 0, which is going to be 2. This part will be 0, because tan of 0 is 0. Secant of 0 is the reciprocal of cosine of 0. Cosine of 0 is 1, so secant of 0 is also 1. So we'll get 2. So now we can build our p sub 3. So p sub 3 of x, we're building this polynomial. Now we've got some zeros here. I'm going to put them in the pattern here just to make sure that we see everything. So we have 0 and then plus 1 multiplied by x minus our center. Center is 0. Let's just put it in just to sort of make sure we see the pattern. So that is going to be our best linear approximation. That's our tangent line. It's just, if you were to simplify it, it'd be p sub 3 of x is equal to x. Now we're adding 0 again, so now it's going to be 0 divided by 2 factorial, which of course is just 0, and then x minus 0 to the 2. And then when we get to our third, we're going to have 2 divided by 3 factorial times x minus 0 cubed. Now this one I am going to simplify because we wrote in a bunch of zeros that are unnecessary. So this is going to end up being x. And then here, if we simplify that, we would have 1/3 x cubed. So that is p sub 3. So we have these two terms that are just 0. That term is 0, that term is 0. So that is our best cubic approximation, third order Taylor polynomial centered at 0. So now they're saying, okay, use this polynomial to approximate this value. So p sub 3 of negative 1/10. Let's write it this way. So we're plugging in negative 1/10. And we're going to have that. So whatever that simplifies to, we get negative 1/10 plus 1/3. Well, I guess we can distribute that minus, or pull that minus out. That minus is going to be preserved. And we're going to have 1 divided by 1,000. So we just have to get to whatever this is going to be. So we can type this into our calculator to get it, or we can get a common denominator of 3,000. So we're going to multiply top and bottom here by 300. End up with that. So our approximation is minus 301 divided by 3,000. So that's the approximation coming from p sub 3. That's our approximation. And then it asks for our absolute error. So absolute just means absolute value. Because your error, you could be a little on the high side, you could be a little on the low side, who cares? We just want to know what that magnitude is. So what we're going to do now we have to use a calculator. So we are just going to go into a calculator and see what the difference in the function value is and that approximation. So all right, so we had tangent of negative 1/10, and then we have whatever the heck that thing is over here. So negative 301 divided by 3,000. And there's our approximation versus our... They said in this instruction, they called it exact value. This still, you all know, when you type that into your calculator, you're still getting an approximation. You know, it's just a better approximation. It's not the exact value. Using that word exact is not really not really the best vernacular. I should probably change that. All right. Oh, and we didn't do the difference yet. Okay, so now we have to find the difference. So let's do it this way. Control copy. Control paste. But we're going to do that. So that is our absolute, well, our absolute error has got to be positive. So if I change it and make that minus and this minus, is that the way to get the absolute difference? No, it's not a minus sign, is it? So there's our absolute error there. So very small. Very small, very small. So we're going to find the difference between them and take the absolute value. That's our absolute error. So we just do one minus the other and then take the absolute value. And that will be our absolute error. Any questions on the concept of the process? Oh, I had the stupid cursor in there. So absolute error is positive. Take the difference, take the absolute value. Okay, so let's try, well, you all try this one. So here, your function is going to be the natural log of x. And what do you think we're going to use for our center in this case? 1. The number closest to 1.05 that you can easily evaluate log and its friends at. All right, so try that one.
N equals 3.
P sub 3, third derivative, yes. Any issues with the derivatives or the values at the center? That all look good? So then we're going to construct our polynomial, p sub 3. So p sub 3 of x will be 0. Let's not put it in this time. We kind of know what we're doing. Now we're putting in a 1 multiplied by x minus the center. So 1 times x minus the center to the first power. And then plus a negative 1. So negative 1 divided by 2 factorial, x minus 1 squared. Don't need the factorial. We'll leave it off this time. And then plus 2 divided by 3 factorial times x minus 1 cubed. So that is p sub 3. And if we wanted to, we could simplify this. We're going to have to plug this into a calculator, so it might be easier just to simplify that anyway. All right, so then we plug it in. Figure out how good, oh, I guess I have to write down what we have. We're plugging in 1.05. So p sub 3 of 1.05. 1.05 minus 1 is 0.05. So we're going to have 0.05 here minus 1/2 times 0.05 squared plus 1/3 times 0.05 cubed. And we'll just type that in our calculator to evaluate it. Too complicated to do it by hand. So we're going to have, let's plug in this log thing. It was log of 1.05.
What I'm going with that, if I remember that properly.
I'm going to call this P. It'll be easier to do the if I call these things, it'll be easier to do the subtraction. This might be smarter to do it this way. So 0.05 minus 0.5 times 0.05 squared plus 1 divided by 3 times 0.05 cubed. And if we do can I just do that subtraction straight up? Now I'm confused. F of x. Nope, doesn't like that. Wait. Doesn't want me to do. Can I do it this way? Oh, are my cap locks on? Oh, that's what's happening. Let's see if we can do this with subtraction. Okay, so obviously we're just going to switch this. If we want it to be positive, we'll make that plus and this minus. That's the same idea. And let's get the cursor out of there. Make sense? There are no mysteries left. All right, so you can see that this error is tiny. And the error gets tiny super fast. We haven't gone that far out. We took 3 derivatives. So these Taylor polynomials are extraordinarily accurate. Makes sense that they're way more accurate than just the tangent line. Calc 1 made such a big deal about this tangent line. It's not very accurate unless you're very close to the point of tangency.
When we're doing this, and let's say we don't have access to Desmos, like it's on a test or something, and P of x, will it either always need to be exact, or is there a certain decimal place like we should go out to before then finding the absolute?
Yeah, this one will always be exact.
Okay.
Because when you do that subtraction, you're always going to get, it's a polynomial. So it's going to, and you're not going to go out too far. So you're just going to be, at worst case scenario, this term here, 0.05 cubed. And on a regular scientific calculator, that's totally fine, right? 0.05 cubed is just a handful of decimals. So yeah, it'll work fine on the test with just a scientific calculator.
Okay.
How would you prefer people to write the higher order derivative? Like a whole bunch of apostrophes like that? Or?
Well, you do, the tradition is you do 3 that way, and then when you get past 3, you put it in parentheses. Yeah, so that's kind of what the agreed upon way is. If you want to put four marks up there, you could. That's fine. But usually what folks do, and most books will do, is they'll go up to 3, but then they'll do the 4. They'll do parentheses up there. Yeah. Yeah. It gets hard to count after a few. But you can do it with just primes if you wanted to. All right. Okay, last slide for Chapter 11, Section 1. All right, so this is what we just did. So the remainder is found by taking the approximation, subtracting from f. That's the remainder. If you want the absolute error, you just put absolute value bars around that. So that's what we just did. Take the difference, but if you want absolute error, same thing as the absolute remainder, you would just take the absolute value of that. So this is one of those remainder things that we're not going to look at in great detail, but we're going to talk about it. This is super interesting. This term, when you look at your Taylor polynomial, your coefficients are found by taking the nth order derivative at the center, which we're going to, a is always the center, divided by n factorial, right? That's the coefficient. And then the multiplication would be x minus a to the n. So when you look at this here, when you look at this coefficient, can you tell me the only thing that's different between this coefficient and our general formula? Yes, it's just the next derivative. That matches, though. It matches our pattern. If we did this, the next one would be, right, the pattern would be the n plus first derivative divided by n plus 1. What's the one difference?
A and C.
A and C. So here, when we're building our Taylor polynomial, each derivative is evaluated at A, and then we do an x minus A. So what this is saying should remind you of the alternating series test, the alternating series remainder thing. Remember that the alternating series remainder thing says go to the first unused term, and that gives you an error approximation of everything in front of it. Right? This is sort of saying the same thing. This is saying go to the next term, one term further, but instead of evaluating this derivative at A, evaluate it at C. And this will give you exactly the remainder. Our alternating series thing was an approximation, right? We went to the first unused term and it approximated if you added everything in front of it up. It gave you an approximation for the error. This is exact. And this mystery C, I mean, the way it's stated just seems very, just plug in C. You cannot find C, though. That's the problem. C is a mystery number somewhere between x and a. It exists, and you can get in advanced calculus, you prove that that C exists, but you cannot find it. And so what we have to do is come up with a way to estimate this coefficient. And the way you estimate that coefficient is to figure out a bound on this n plus first derivative. So if we can figure out a bound on this derivative, then it will act a little bit more like we had with the alternating series remainder. We had an estimate for that remainder, for that error. So what did I just do? I slid something. So the idea here is that you have to find a bound on that function, and that's what the capital M is. The capital M is a bound on that remainder, on that derivative function right there. And so then you're just going to replace this numerator up here with whatever that M is. So the m plus 1 factorial just got moved over here, and we're just replacing that m plus first derivative at c with this bound. Now, for us, in the homework, there's a couple that are going to ask you for this m. We are really going to just focus on the alternating series, so it's not a huge deal. But there are a couple homework problems. I won't put this on the test, though. So this m plus first derivative is just a function, right? And so if this c value is somewhere between x and a, all you have to do is plug in your x value there, plug in your a value there, and just see where it's biggest to find the bound. So there are a couple homeworks on it, but we won't put it on a test because it's a little beyond what we need in this class. Okay, so let's go to our next section, properties of power series. And this section is going to allow us to create series instead of just polynomials. So we'll see that we have this extra piece at the end. We basically have our Taylor polynomial and put a plus dot dot dot, and we have what's called a Taylor series, which is an example of a power series. Power series, again, is a series of powers of x, never-ending polynomial. So our first one is going to be geometric series. When we first introduced the geometric series, we started with this expanded form, and we figured out that if r had a magnitude less than 1, that the sum was 1 over 1 minus r. So we did that last chapter. Now we're just switching our perspective, and we're going to say, hey, if we replace this r with an x, we now have a function. 1 over 1 minus x is a hyperbola. It's a function. And that function, if we change all the r's to x's, we can just change our perspective and say, oh, we are taking this function and expanding it into a never-ending polynomial. So this function, 1 over 1 minus x, if we were to graph that function and then graph this never-ending polynomial, they would match on this interval, on the interval negative 1 to 1. That's our domain. Okay, so that's our new perspective. Now we're going to be thinking about starting with a function and having our never-ending polynomial, our power series, equal to that function, generally on some interval. Maybe it's the whole real line, but maybe it's a restricted interval. So we think of this as the domain over here. In the context of power series, we're going to call this the interval of convergence instead of the domain, but it means the same thing. Domain means the set of x's for which the function is defined. That's what it means here. For a power series to be defined, it means that it converges. And if it diverges, that's not that useful to us. So that's our new perspective, starting with function, building polynomial, in never-ending polynomial. So power series has this form. We've got coefficients. The c sub k's are coefficients. And then we have our shifted power of x. So the center is a. If the center happens to be 0, then it's just x to the k. But if the center is not 0, like we just saw with our Taylor polynomials, we have that shifted thing going on. Now this is the part that gets interesting. So we've got our coefficients. We have the center. There is going to be this interval of convergence centered at A. All right? So whatever the center is, the interval of convergence is going to straddle it. It's going to be symmetric about A. This is not obvious. When you have the center of your power series, it's not obvious that the x's to the left and the right are going to be equal in terms of convergence. Like it feels like, oh, it could converge, further out on this side and less out on this side. No, that's not what's going to happen. With a power series centered at A, the x's that cause convergence are going to be symmetric about that center. always. We're going to call that the interval of convergence. Capital R is going to be called the radius of convergence. So we're going to go R to the right and R to the left of the center. Have you ever heard the word radius associated with an interval? What do you think of when you hear the word radius?
A circle.
A circle. And so this is what's interesting. We're calling it a radius. And the reason it's called a radius, when you go into advanced calculus and you take a complex analysis class, it turns out that if you go into the complex numbers, and hopefully you're all semi-familiar with the complex numbers, this would be I in the complex plane. 1 is right there. -1 is to the left. You know, this is going to be -I. This is the complex plane, the set of complex numbers. Well, it turns out that if you take these crazy power series and you let that x not just be a real number, but you let it be a complex number, you let it be imaginary, turns out that whatever that radius, whatever this corresponds to, really it's corresponding to a disk of convergence and not just an interval of convergence. If you imagine this extending into a big circle and going up and down are the imaginary units, if you go up Ri and minus Ri, you will get convergence for any of the complex numbers that are within the circle. So if this interval here was from -1 to 1, like it is for the geometric series, and you start plugging in -0.1 plus 0.1i, you'll get convergence. So you can plug in all the imaginary numbers that are within that disk, and you will get a convergent series, which is a little bit mind-blowing. So that's why we call it the radius of convergence, because there really is a circle or a disk of convergence. Okay, now the endpoints are a little squirrely. At these endpoints, there is sometimes convergence at only one endpoint, and there is sometimes convergence at both, and sometimes convergence at neither. So those have to be tested separately. This is going to be where the bulk of our work is, dealing with these endpoints that can be squirrely. So if we have a power series, let's just look down at this note for a second. If our center were 3 and our radius of convergence was 4, from 3 we could go 4 to the right or 4 to the left. That would satisfy this condition. There are 4 possible intervals of convergence. The interval of convergence will be from whatever the endpoints are, -1 and 7. But then we have to test each side of the interval and figure out, do we have convergence at -1? If so, we include the -1. Do we have convergence at 7? If we do, we include the 7. And if we don't have convergence, we put a parenthesis where it's not converging. So all 4 of these are candidates for the interval of convergence if the center is 3 and the radius is 4. Okay, so that's going to be, again, that's going to be sort of the bulk of our work is going to be dealing with these endpoints. So when we have our power series here, centered at A, first and foremost, every power series converges at its center. And that should be totally obvious. So it should be totally obvious because when you plug in the center for the x right here, what do you get inside the parentheses? 0. Right? You get A minus A. So the only time you don't have a term with that x minus A in it is when k is 0. Right? When k is 0, x minus A to the 0, that's gone. So it's just that very first constant, the c sub 0. When you think about our geometric series, 1 plus x squared, etc., right, that constant of 1 is what's going to remain if you turn all the terms that have an x into 0. The only thing that remains is that leading constant. So every power series is going to converge at its center because the value at its center is whatever the leading constant is. All right? And we are going to have absolute convergence for all x. So there's three possibilities. We have absolute convergence for all x, which means the radius of convergence is infinite and the interval of convergence is the whole real line. So that's one option. So if it converges for all x, we say the radius of convergence is infinity. It's just infinite interval. Next possibility, which is the one that takes the most work, is the series converges for a group of x's that satisfy this inequality, and it diverges if you're beyond. So just like that picture on the last slide, the interval of convergence was that red interval. You have divergence outside of the interval of convergence. And then the simplest case I just mentioned, the series converges only at the center, giving a radius of convergence of 0. If a power series converges only at its center, that's an interval, a degenerate interval. We say the radius of convergence is 0. So radius of convergence 0 means a single point of convergence. Radius equal infinity means all real numbers convergence. And then we have our stuff in between. Now, how the heck do we find this capital R? Well, that capital R is going to be determined by using either the ratio test or the root test. 90% of the time we use the ratio test. But sometimes we can use the root test. The ratio test is the most important test for power series convergence. So let's try one. There's power series. So when you think about a power series, you should be thinking of an infinite collection of infinite series. Every single x that you plug in here, other than the center, because the center everything turns to 0 except the leading constant. But every x essentially that you plug in there creates an infinite series of numbers. If you plug in 4 for that x, you have an infinite series of numbers. If you plug in a 4, you would have 3 to the k over k factorial. We analyzed that in the last chapter with the ratio test, because there's a factorial. If you plug in 10, you would have 9 to the k over k factorial. Powers, that's an infinite series of numbers. That's like what we did in chapter 10. So when you think about a power series, every single x is creating this infinite series. So you have all these infinite series coming out of this thing. Right? Every value of x is causing an infinite series of numbers. So a power series is an infinite collection of infinite series. Tons going on. Okay, now to find the radius of convergence and the IOC, the interval of convergence, for the following power series. That's what we want to do. So the radius of convergence and the interval of convergence. We're going to use the ratio test. The ratio test has an absolute value in it. That's why we are getting absolute convergence. So the ratio test says that R is equal to the limit as k goes to infinity of the absolute value of a sub k plus 1 divided by the absolute value of a sub k. So our a sub k is the entire quantity in here. Right? This is our a sub k, this whole thing, including the x's. The whole thing is a sub k. So we're going to form our limit as k goes to infinity. A sub k plus 1, and we have to put absolute values, and there's an x in here. X is just a real number, so it could definitely cause some negatives. So we are going to need that absolute value in the numerator. In the denominator, k plus 1 factorial, that's not negative. So there is a sub k plus 1 with absolute value. So absolute a sub k plus 1. Dividing by the absolute value of a sub k means multiplying by the reciprocal. We don't need the absolute value on the k factorial, but we do on this numerator because what if x is 0? What if x is negative 5? You're creating negative numbers there. So we have that. So there is our limit that's going to determine our radius of convergence. So now we're going to do what we did in chapter 10 and simplify. The only difference is that we've got some x's in here now. So how many x minus 1s and where? Did you say 1x minus 1
Yes.
in the numerator?
Yes.
And we have the absolute value of it. Everybody agree? Because we have k plus 1 x minus 1s on the top, k x minus 1s on the bottom, so they all cancel except for 1. We still have the absolute value, though. All right, how about the k factorial and the k plus 1 factorial? What's left? Just k plus 1 in the bottom, right? Because k plus 1 factorial is k plus 1 multiplied by k factorial. The k factorials will cancel. So we have 1 k plus 1 left. This limit is as k goes to infinity. Are there any k's in the numerator? Nope. So let's factor that out. That numerator is constant with respect to k. So that x factor can come out to the front, and we have this. And what is that limit? What's the limit of 1 over k plus 1? 0. 0 multiplied by anything is 0. So that's 0. Okay. All right, 1 over k plus 1 goes to 0. 0 times anything, 0 times x is 0. Now remember the ratio test conclusion. Geometric series, ratio test, root test. Now we have to ask ourselves, when is this less than 1? When is this less than 1? Are there any x's for which that is not less than 1? No, because we multiplied by 0. So it doesn't matter. If you plug in x equals 10,000, if you plug in x equals negative 1,000,000, it doesn't matter. This limit's still 0. So this limit is 0 for every single x that you could plug in there. It's going to be 0. So if this is always true. It's true for all x. This is true for all x. So that tells us two things. It tells us that our radius of convergence is infinity. Because it's true for all x, that means it converges for all x, converges absolutely for all x. And it tells us that our interval of convergence is the entire real line. So we have both r and I coming from that result. So this is one of our edge cases, where it's true for all x. So we have a big radius of convergence. Okay, let's try this one. So again, we're going to use the ratio test. We always default to the ratio test with power series, unless it's obviously a candidate for the root test. If there's a factorial, we're definitely still sticking with the ratio test. If there were no factorial, then we could opt for the root test. Okay, so our ratio. So again, its limit is k goes to infinity. Absolute a sub k plus 1 divided by absolute a sub k. So this will be the limit of, so the numerator is going to be k plus 1 factorial, and then we need our absolute value, and we're going to have x minus 10 raised to the k plus 1, close the absolute value. So there's a sub k plus 1. Absolute value. of a sub k plus 1. And then we divide by absolute a sub k. Absolute a sub k, we have the k factorial, and then we have the part that could be negative, so we have to have absolute value bars. So we have that. We go through our simplification process. We're going to have a k plus 1 in the numerator. K plus 1 factorial will cancel out the k factorial, leaving k plus 1. We have one extra x minus 10 inside absolute value. Once again, the x minus 10 absolute value does not depend on k, so we can factor it out to the front. And then we're taking the limit of k plus 1 as k goes to infinity. All right, so what's that limit equal to? That is going to be infinite. So when is this less than 1?
10. X equals 10.
So there's one subtlety here. We already have it in the bag that this converges at 10. Right? That's going to converge at 10. And so here, if we wanted to be super nitpicky, we would say that this is infinity for all x except 10. 10, you would have 0 multiplied by infinity, which is an indeterminate form. We're not going to get nitpicky, though, because we know we have convergence at 10 already. So when we see this, we are going to say to ourselves that this is never true, although we do know that we have convergence at 10. We're just going to be a little bit sloppy here. We're going to say that's never true. Therefore, we have, if that's never true, the radius of convergence is 0. And the interval of convergence is just a singleton point. That singleton point in this case being 10. So, a little bit sloppy there. When we say never, we mean no x other than the center. So those are the two edge cases where we have a degenerate interval of convergence, just a point, and we have the entire real line as the interval of convergence. So those are the two extreme cases. So let's go ahead and take our 10-minute break, and then we'll do the more complicated cases where we have to calculate endpoint behavior. Sam?
So, talk about this. No, stop it. Can you take the volume of that disk?
Wait, volume of a disk? So let's go ahead and do one of these ones that are much more complicated. Okay, so we're staring at a power series. Remember that you want to identify it as a power series as soon as you see the x. You have an infinite series, and as soon as you look inside and you see, oh, there's an x in there, that's when it is not just an infinite series. When we say infinite series, we usually mean of numbers. If we want to indicate that it's actually a power series, or it's got an x in it, we say power series instead of just infinite series. So power series has an x in it. And we want to analyze that. We can use the root test or the ratio test. Doesn't really matter in this case. There's no factorial, so we could use the root test. Either one's going to be fine. So let's go ahead and use the root test here. So this book usually uses a row for root test instead of just the R. It's still absolute value. Well, we have limit too. So, but it is still absolute value. So limit as k goes to infinity. Kth root of the absolute value of a sub k. So there is the root test, same as it always was. Doesn't look any different. Now here, when we go to plug in to figure out what's inside the kth root, we are taking absolute value. So the minus 1 to the k, which is a switch, that just goes away. Absolute value is going to take that away. We still need the absolute value around the x, though. Because x is just a real number. Could be positive, could be negative, so we still need the absolute value around the x. So absolute value will definitely take that away, but then it's going to zoom in just on the x, which is the part that could be negative. Well, kth root of all this business simplifies it very nicely to absolute x divided by 4. Take the kth root of the numerator, kth root of the denominator. Those two powers of k are going to vanish. So we have that. Say again? I think what you said is insightful. So it is constant. There is no k in here, right? So we can cut right to the chase here and say, we can say that, because that's constant with respect to k. There's no k there. So that is itself. The limit is itself. Okay? Now here's where the nitty-gritty starts happening. Now we see that we're not in one of those two edge cases where we got 0 or infinity. Now we see that some of the x's are going to cause that inequality to be true, and some of the x's are going to cause it to be false. And right off the bat, you think, okay, if I plug in 16, 16 divided by 4 is 4, that's not bigger than 1, right? So we can easily see numbers that are not in the interval of convergence and numbers that are in the interval of convergence. If we plug in 3, 3/4 less than 1, yeah. So 3 is in the interval of convergence. So now we have to figure out, okay, well, what are the numbers in this interval of convergence? So we're going to carry on our merry way and just solve this inequality. We're going to have absolute x. We can multiply both sides by 4. So we have that. So what this tells us instantaneously is that our interval of convergence, we've just put the radius in the interval here. So it tells us that the center is 0, and it tells us that we can go 4 to the left or 4 to the right. So what do you think the radius of convergence will be then? If we can go 4 to the left and 4 to the right, the radius of convergence is 4. When you get to this point where you have x isolated, that number, if you have x isolated, just absolute x here all by itself, not 2 absolute x, just absolute x, that is always the radius of convergence. You can visualize the center is 0, and you're going 4 this direction and 4 this direction, so the radius is 4. And it also tells us that the interval of convergence, we know this much about the interval of convergence. We know the goalposts, but we don't know whether we include them or exclude them.
By technicality, our less than greater than should have a equal to.
Say where?
Should the inequality have an equal?
This is strict.
That is strict.
This is finding, because we know that for the geometric series, the root test and the ratio test, less than 1 converges, greater than 1 diverges, and equal to 1 is inconclusive.
Right.
So we're trying to find convergence, so we want to know when is it less than 1. So these are the x's for which it's less than 1. Now, the endpoints are just treated differently. We know for sure that if we're between -4 and 4, we have absolute convergence. And we just test the endpoints as a separate thing.
Yeah.
So it's not because of the inequality, it's because we actually zero in and test those. So now we have to go test them. So here is the monkey on our back testing these things. So we have 4 and -4. We have to test both of those. So let's go ahead and test -4 first. Let's give ourselves a little more space. So we're going to test -4 first. This brings us back to chapter 10. So come in here and test x equals -4. So we're going to go to the infinite series, up there, the power series. And we're going to plug in -4. And when we plug in -4, we will have a series of numbers. And we're back in chapter 10, doing all that stuff from chapter 10. So there's our series of numbers. We just have to analyze that and figure out, does that thing converge? Does that thing diverge? Let me move it up here just so we can try to do both endpoints on one page. So let's go ahead and see if we can simplify this. -1 to the k. And then if we bust this apart, we have another -1 to the k. And then over here, we have 4 to the k over 4 to the k. Is that all okay? So -4 quantity to the k. We take that power of k here, and we push it onto the -1, giving us the second -1 to the k. And we push it onto the 4, giving a second 4 to the k. These, of course, are going to cancel each other out. And what is the exponent on -1 going to be? 2k. And what is -1 to the 2?
1.
1. And what's 1 to the k? 1, right? 1 to any power is 1. So that all reduces to that. All right, so remember this right here, 2k is the power, so you can do the 2 first. That 2 squares the 1, giving a 1 to the k, but 1 to the k is just 1. 1 to the k.
Do we not have to worry about it touching and being like 1 to the infinity?
No, because these k's are one at a time.
Okay.
The limit we might have to worry about. If we were taking a limit, yeah, if we had a limit of 1 to the infinity, then it would be indeterminate. But that series, no term is going to have an infinite power.
Okay.
Right? The powers are getting bigger and bigger and bigger, but it's not like we have a limit of something that's of the form 1 to the infinity. If we were taking a limit, then we'd have to worry about the indeterminate form. And does that series converge or diverge? Diverge. 1 plus 1 plus 1 forever, diverging. All right. So now what would your justification be?
The divergence test?
Correct. So this is diverging by the divergence test. When we are testing endpoints, you don't have to get into the nitty-gritty. You don't need to say a sub k equals 1. Limit of a sub k is not equal to 0, therefore can diverge by divergence. You don't have to do all that. When we are just analyzing endpoints, it's sufficient to just cut to the chase. Just say that it diverges and why. You don't have to actually go through the, like, in chapter 10, if the question, like on the worksheets, say analyze using divergence test, then you've got to get into the nitty-gritty. The limit of a sub k is the limit of 1 as k goes to infinity. That's not equal to 0, therefore it diverges. If it's just an endpoint that you're testing, you can just cut to the chase as soon as it's obvious. Okay, now let's test 4. So what we can do now over here is put a parenthesis right there, because we now showed that we have divergence at -4. So now let's plug in +4. So if we plug in +4, we have that. Plugging in +4 up here, we've got that. Once again, we have these 4 raised to the k powers canceling and giving 1. So our series is -1 to the k. Multiplied by 1, we don't need to put the multiplication by 1 in there. And so then the question is, does this series converge or diverge?
Diverge?
So that series, if you were to write it out, and it depends a little bit on whether it starts with 0 or 1, but it doesn't matter, right? We all know that if you chop off the first leading terms, it doesn't change convergence or divergence. So when you're visualizing this series, if you don't have a subscript right there, it's either 1, -1 plus 1, -1 plus 1, -1 plus 1, or maybe it starts with -1, but then +1, -1 plus 1, right? So it's going to, in this particular case, because it does start at 0, it's going to have this form, 1 -1 plus 1 -1 plus 1, etc. So this diverges, and what would your why would it diverge?
Because it's oscillating?
It's diverging by oscillation, you could say that. It's, if we were to get into the nitty gritty, what kind of series is this?
Geometric.
Alternating series. Alternating series. So alternating series. Yes, you could say it's geometric. You can go down the geometric route. If we see the switch in there, generally we would call that alternating. You could go geometric though for sure. And if you went geometric, what is the R value?
-1.
-1. And that's not less than 1 in magnitude, so it diverges. If you go the alternating series route, what would your justification be?
The limit as k goes to infinity isn't 0.
Right, divergence test. Yep, divergence test. So you could say either. Yeah, it's totally fine. I've never even really thought about that as using geometric, but you absolutely could use geometric, where your R value is -1. So diverge by either divergence test. That's the one I think is a little more obvious because the limit is not 0. The limit of a sub k is not 0. But you certainly can do geometric series also. So you just have to say by something. Divergence test or geometric series, GS, something. So this is now we are at the point of conclusion. That is our interval of convergence. So we have divergence at both those goalposts, both the endpoints. All right, let's try another one of these. Now, this one looks a little harder to do the root test with, so let's go our traditional ratio test. So we're going to let R be the limit as k goes to infinity. Absolute a sub k plus 1 divided by absolute a sub k. Once again, the absolute value is going to squash the switch. That thing's going to be gone. So we're going to have absolute k, x to the k plus 1 over square root k plus 1. So there's the absolute value of a sub k plus 1. And then dividing by a sub k's absolute value means multiply by its reciprocal. So we'll have the square root of k up top. We'll have absolute x to the k down below. And then we simplify. So let's do the x's last. Let's do the square root. Square root of k over k plus 1. I'm going to group those two together. And then we're left with 1x in the numerator, so we could write it like that. Now we can cut to the chase and write the limit now. You don't have to factor out this absolute value of x. That's not necessary. It's important to understand that you could do that though, right? Because there's no k in this x quantity here, so that could factor to the front. So this whole limit is determined by just this portion that has k's in it. And what is the limit of that square root of k over k plus 1? 1. Everyone agree with that? Because the limit can jump inside this fraction. It can jump inside the square root, and we're just taking the limit of the fraction. We have a linear in the top, a linear in the bottom. We could divide by k. We could say the powers are equal. Leading coefficient ratio is what the limit is. So bottom line is the limit of this piece is 1. This is constant with respect to k. Since this limit is as k goes to infinity, has nothing to do with x, we're going to get 1 times absolute value of x. So we get that. So that is our limit. And then, same thing that we've been doing, we say, when is that less than 1? And this is going to imply a couple of things. It's instantly going to tell us that our radius of convergence is 1, and it's instantly going to tell us that our goalposts, our endpoints, are -1 and 1. Is everybody okay up to that moment? So now we have to go in and test those endpoints. We know that the radius of convergence is 1. We know the interval is going to go from -1 to 1, but we just don't know what happens at those endpoints. So we're going to test each one. When we plug in -1, we have an infinite series of numbers. Does it converge or diverge? That brings us back to chapter 10. All right, so let's test. Let's use purple for testing. So we're going to test x equals -1. So we're going up to our series. We're going to replace the x with -1. So we have our leading factor out there, our switch. And then we plug in -1. We get -1 to the k, square root k. We're going to combine the -1s. So combining those is going to give -1 to the 2k. And what is -1 to the 2k? How does that simplify? It's just 1, yeah. Right, because -1, when we have a power, we have a product up here, we could, if you have some number like a raised to the ab, you can do whichever one you want first. You can do that, or you could do that. And so let's do the square first. -1 squared is 1. And then 1 raised to the k, 1 raised to any power is 1. So this is going to be 1 over that. Okay, what kind of series is that? It's a p series. Converge or diverge? Diverge. So here we just say p is equal to 1/2 less than 1, therefore diverge.
Could we do the divergence test also? Or-
No.
Okay.
Well, we could try it. What happens with the divergence test? What is the limit of this as k goes to infinity?
0.
0.
Oh, so it's incorrect.
So it's inconclusive, yeah. No, it's absolutely something to think about, right? And having the divergence test close at hand is good. Often it's inconclusive, which is fine. You just dig deeper. But everyone see the divergence test would be inconclusive? Because the limit as k goes to infinity of our a sub k is going to be 0, which means it might converge, but it doesn't converge in this case because it's a p series with p less than 1. So not going to converge. So that puts us in this position here where we have divergence at -1, so now we have the left endpoint filled in. Or maybe I shouldn't say filled in. The left endpoint excluded. And then we're going to go to 1. So when we go to 1, we have -1 to the k. And we have that. All right. What kind of series is this? Alternates. So that's an alternating series. Now here, the nitty-gritty, we would go to the alternating series test, but we don't have to get that particular when we're dealing with endpoints. It's enough to cut to the chase. We don't have to get super precise. Is this going to converge or diverge? So this is going to converge by AST. Remember the 2 steps of the alternating series test. The limit of 1 over k to the half, that limit is 0. So the divergence test is inconclusive. And the alternating series test essentially says if the a sub k's have a limit of 0 and are decreasing, we have convergence. Is this a decreasing function? Yes, the numerator is constant, and the denominator keeps getting bigger, so the fractions keep getting smaller. Now, we don't have to write all that down. When we're just dealing with an endpoint, we can be very concise. We don't have to go through both pieces of the alternating series test. There's too much. There's already plenty of work. So that's going to converge. So now we've concluded the 2 things that we need for a power series: the radius of convergence and the interval of convergence. So it's going to be super important with these, especially with this alternating series type thing, to have a good idea of when your alternating series are converging and diverging. All right, so with an alternating series, as long as the a sub k's are going to 0, and the a sub k's are decreasing, you have convergence.
Shouldn't it be 1 to the k over root k?
Yes, but what is 1 to the k?
Oh, just. Okay.
Yeah, 1 to the k will be 1. So everyone agree with that? So when we think about 1 to the k and we're multiplying 1 by itself repeatedly, it's always going to stay at 1. So 1 to the k is always going to be 1. All right. Well, let's take a look at, okay, let's up the ante a little bit. It's getting too easy. Okay. So there are 3 standard ways. Combining is something we always do, right? We add things together, we multiply things, we divide things, whatever, we combine them. And there are 3 standard ways to combine power series and create new power series. There are 3 ways that we can do things that lead us to some nice conclusions. Now, the examples we've seen, we haven't had any really nasty endpoint testing yet, but you can see that the endpoint testing is a little onerous. There are some ways that we can avoid endpoint testing. So, we'll see that as we look at our 3 possible ways to combine series here. Simplest, if we have 2 series that converge, 2 power series that converge to these functions, f and g. So this power series converges to the function f, this power series converges to the function g. Well, if you add or subtract, the sum or difference is also going to converge, and it's going to converge to what we would like it to converge to, f plus g or f minus g. So that one's easy. And whatever the interval of convergence is, if both of those series have the same interval of convergence, this new sum or difference, same interval of convergence. So if we start with 2 power series that have an infinite radius of convergence, we end with a sum or difference that still has that infinite radius of convergence. So that one's the easy one. Now this one, okay. So multiplication by a power of x. So we have this power series here that is converging to f already, right? That power series is converging to the function f. If we multiply by a power of x, we can just slide it inside. There's no k on this thing out here, so it's constant with respect to k. It can just slide inside and create an exponent inside that's x to the k plus m. This is going to converge to the function multiplied by x to the m. So we have this power series converges to f. If we multiply by x to the m, we multiply by x to the m. We multiply f by x to the m also. Okay. Now the part here that is a little funny, this says for all x and I, if m is an integer such that m is greater than 0. So if m is greater than 0, there's no funny business because there's no potential division by 0 out in front. Right? So if m is a positive number, that x to the m is never undefined. Everyone agree with that? So there's no funny business there. Now, if m is an integer such that m is less than 0, then you have to deal with this when x is equal to 0. It converges to whatever that limit is. Because there is division by 0, if this m is negative, then you have 1 over x squared, whatever it is. All right? We are not going to see that case very often, if at all. Can you understand why they might need to distinguish this? Or let's at least talk about why this is true. When we say that something is a power series, it's a never-ending polynomial. The exponents on a polynomial can never be negative. Right? Everyone agree with that? Polynomial, oh, powers are always non-negative. So you may say to yourself, well, if we multiply by, say, 1 over x squared and pull that x squared in there, you theoretically could end up with x's to a negative power. Right? If this was the geometric series where we had 1 plus x squared, if we multiply by 1 over x squared, we'd have an x over x squared, which is going to end up being a 1 over x, which is not a power series. So there's an implication here that they have not really laid out clearly, and that is the only time this ever can happen is if your power series has, it doesn't have all of the terms that we are sort of accustomed to seeing, like the 1 plus x squared. Because if you take that and you divide by x squared, now you don't have a power series anymore because you have negative exponents. So the only way this could happen is if you've got some wild power series that starts with, say, x to the 4th. Maybe it's x to the 4th plus x to the 8th plus x to the 12th. Then you could take 1 over x squared, move it inside, and still have a power series. So power series, you always have to have positive exponents or 0. But anyway, it's not a case that we're going to pay much attention to, but that's why that is there, because you could be dividing by x here. And if you're dividing by x, it's undefined, so you have to take a limit. All right. Now, the nice thing about this case up here, and the part that's going to be most important to us, is that the interval of convergence does not change. Does not change. Let's think about that for a moment. When we use the ratio test, we have a sub k plus 1 divided by a sub k. If you multiply by x to the m to create your a sub k, you're also multiplying by your x sub n when you create your a sub k plus 1. And those x to the m's just cancel. Right? If you have an a sub k right here, if you multiply by x to the m for your a sub k, when you create your a sub k plus 1, there's no k in the x to the m. So you're going to end up with an x to the m in both top and bottom. They cancel out, so it's not going to affect the interval of convergence. It's very similar to, we had seen earlier that if you multiply a power series by a constant, it also does not change the interval of convergence. If you have a power series and it converges, and we multiply it by a constant out in front, or even a series of numbers. If we have a series of numbers that converges and we multiply by 5, it's still going to converge, and it's not going to change what it converges to, the series part of it. The series part of it will still converge to the same thing. OK, so let's look at an example, or let's talk about the last case. So the last case, there is a modification of I. This one is the composition one. And what we're doing is just taking, we've got our power series right there. We're going to replace the x with a composition. We're going to take some other function and just stick it inside there. And if you do a replacement, and we've done this with the geometric series in the past, if you do a substitution into the series, you also do the same substitution into the interval of convergence. So we've seen this before. If you replace the x with x squared in the series, or, well, let me think about that. Let me restate what I was just about to say. If you have a series and if you replace x with x squared, you go to your interval of convergence and you replace x with x squared also. Right? You just do the same thing in both places. So let's try these. OK, so here we have geometric series. So this is going to be the middle case up there. What did we multiply this geometric series by?
X cubed.
X cubed. So power of x. So the power series here for this new function g, the power series is very simple to create. All we do, it always sounds worse than it is. All we do is multiply this by x cubed. So we're going to multiply x to the k by x cubed, and we're going to get that. Right? So on the left side, we multiplied by x cubed. Up here, if we multiply that by x cubed, we get this. So g is x cubed times f. Well, if we multiply the left side by x cubed, we multiply the right side by x cubed. And if you multiply the right side by x cubed, you can add those powers on the x together. And this is our new power series. And the interval of convergence does not change. So that is case 2 that we just talked about. That's how it's implemented. That's it. So if you multiply by the power of x, move it to the inside, interval of convergence does not change. Okay, how about this one? This one is case 3. When we look to the left side, what did we replace x with?
X cubed.
X cubed. We're replacing x with x cubed, not multiplying by it, but we're replacing it. And so we do the same thing on the right side, the part that has the power series representation. So we come inside here. We replace x with x cubed to the k. That's x to the 3k. Now here, the interval of convergence changes. The interval of convergence was -1 less than x less than 1. But we replace the x with x cubed, so we have to come in here and replace that x with x cubed in order to calculate the new, or potentially new, interval of convergence. Now in this case, you can take the cubed root of all 3 sides, all the way through. Cubed root of -1 is -1, cubed root of 1 is 1, cubed root of x cubed is x. So this interval of convergence didn't change, but that's a coincidence that it didn't change. It didn't change because the cubed root of the interval created the same interval. Okay, so, but when we substitute into the function part of it, we have to also substitute in the same way into the interval of convergence. So we're going to replace x with x cubed. So those are the second and the third ones. Let's try another one here. So we've got a power series given to us for that expression. What are we doing to create the function g? Multiplying by?
Power of x.
Multiply by a power of x, x squared in particular. So we're multiplying by a power of x. So the power series for this function g, we're going to take the power series for the function natural log of 1 minus x. We're going to multiply by x squared. So we just come inside. If we multiply by x squared, we get that. Does the interval of convergence change when you multiply by a power of x? No. So that's it. Nothing too crazy. So let's do a substitution again, or a composition. So what are we replacing x with in this case? There's x. We're replacing it with x to the 4th. So the power series representation, we come inside. And we're going to replace this x with x to the 4th. If we replace that x with x to the 4th, we get x to the 4k. So there's the power series representation. Now we have to come over to the interval of convergence. The interval of convergence was that. Now we have to replace x with x to the 4th. So we're replacing x with x to the fourth. Okay, now we have to solve this inequality. There are a couple of ways to do it. We've looked at something similar to this before. Let's do it two ways. Let's look at it visually. So if we look at a graph of x to the fourth, x to the fourth is, it kind of looks like a parabola, but it's a little extra flat down here. So it looks like that. And we want it to be between, so that's the function, f of x equals x to the fourth. That's the black function I have here. We want to know when are the function values in between -1 and 1. So we want to know what the corresponding x's are that give us function values in this interval. What are the x values that cause x squared to be between -1 and 1? What does x, what is true about x? So the x's are down here,
Between -1 and 1.
including or excluding x endpoints.
Including.
So if I plug in -1 right here, I'm up here at +1. Is that true?
No.
No.
Okay.
So we're not going to include that endpoint. Are we going to include this endpoint?
Yes.
No. Because if this function right here is y equals x to the fourth, what is the function value if you plug in 1 or -1?
1.
And does 1 satisfy this inequality?
No.
This is a compound inequality, so both sides have to be true. So 1, if you plug in the 1 in the middle here, 1 less than 1, false. Okay, so that's the visual way to do it. That says that x is going to be trapped in between -1 and 1, not including the endpoint. So the interval of convergence here, in fact, changed. We lost convergence at the left endpoint. So that's the geometric visual way to do it. You're trying to figure out the x's that put you inside this interval right here. Well, the x's that put you inside the interval, they don't include the -1 or the 1. So we're just looking at this open interval right there. Now, if you do it this mathematical way, which is not always obvious, but I think it's a totally legitimate way to do it. Do you agree that this side of the inequality is always true? This is x to the fourth right here. That's x to the fourth. And if we're only, we're dealing with this is a negative number right here. Let me think about that. Let me think for one moment here before I say what I was about to say. Yeah. Do you agree that this is always true no matter what? For a second there, I was panicking about fractional x's. Let's look at a fractional x, like 1/2. It doesn't matter if it's fractional because this is never negative. Right? X to the fourth is always 0 or more. So this side is true no matter what. So this is a compound inequality, so both sides have to simultaneously be true. The left side is always true. Is there any disagreement with that or any question on that? Right? No matter what you plug in here, you plug in 0. 0 is greater than or equal to -1. That's true. Plug in 10. 10 to the fourth is bigger than it. Any positive number is bigger than -1. We all agree? So that's going to be true no matter what. So the solution to this inequality is equivalent to the solution of that inequality. So this inequality and this inequality are going to have the same solutions because this side's always true. This doesn't add any extra x's. Now, what is the square root of x squared?
X.
Close.
Plus, yeah, this side.
The square root of x squared is
Plus or minus x.
absolute value of x. Because x could be negative or positive. Do we all agree with that? Like if I plugged in -3 here, -3 squared is 9. This symbol means the positive square root of x. It does not mean plus or minus. That symbol means positive square root. So if we plugged in -3 here, we'd have -3 squared, which is 9. Positive square root of 9 is 3, which is not what x is. It's the absolute value of x. So we can do a similar thing down here, where we take the 4th root of both sides. The important thing is that you have an even index. And what do you think the 4th root of x to the 4th is? Absolute value of x, for the exact same reason. So this is absolute value of x. The positive 4th root of 1 is 1. And we're back to the same situation, that x has to be between -1 and 1, not including the endpoints. So you can do it that algebraic way, or you can do it that graphical way.
Initially, why can't you take the 4th root of -1? I know that doesn't work out, but why, like, logically doesn't it work?
Exactly because of what you just said.
Yeah.
The 4th root of -1 is undefined. So if we have an inequality like this and we're taking an odd root, you can do an odd root of all three pieces. But if you have an even root, you can't do an even root of all three
Is it
pieces.
because we're only on, like, the real number plane?
Yes.
If we were to be on the imaginary number plane, would you be able to do that? Or
No, you still can't do that.
Still can't do that?
Still can't do that. Yeah, yeah. Now, if this interval was all shifted and we're dealing with positives, then you could. Like if this interval went from 1 to 4, then you could take square roots all the way across.
So even in advance, when you have the real number line and the imaginary, you still can't solve by taking the 4th root of both sides?
Yeah, you can't.
No. Okay.
So here's why. Bless you. When you're dealing with the imaginary numbers, you have a circle. You would have to test every single point on that circle. So you don't have an interval of convergence. You have a circle of convergence. And so what they do in complex analysis is not even really look at that circle because there's an infinite number of points. So the end points are infinite. So you can't even do it. But yeah, so we have a geometric way and we have an algebraic way. Is there any questions on this algebraic way? So this is a super key fact, though. The square root of x squared is not just x, it's absolute x. All right. All right, hardest problem in the section. Well, no, we're not to the hardest one yet. We're getting there. Next slide. So we just talked about 3 ways we can take power series and create new ones. We can multiply by a power of x. We have the boring one where you add or subtract. That one's not that, we don't see it that much. Multiply by a power of x, or you do a composition. All right. 2 new ways you can differentiate or integrate. These things are polynomials. We know how to differentiate and integrate polynomials. So this says we've got a power series, converges to f on the interval. Now, they didn't use the word converge here. There's some subtleties we're not going to talk about right now. But when we see a power series and we see the function f, we think of them as indistinguishable. They're the same thing. OK, so if f is differentiable, then you can differentiate the power. The power series is easily differentiable because it's a polynomial. So as long as the function is differentiable, we can also differentiate the power series. So if we've got this power series there, to differentiate it, you pop the k down and subtract 1. That's how you differentiate a polynomial. The derivative of x to the 4th, 4x cubed. So all you do is pull the power down, subtract 1 from the exponent. That's what they're showing us here. And interval of convergence. What we will have is the same radius of convergence, but when you differentiate or when you integrate, you will have the same radius of convergence, but the endpoints could have behavior that changes. So unfortunately, when you differentiate or integrate, you do have to retest endpoints. So with that last slide, if you multiply by a power of x, you don't have to do anything. If you do a composition, you just push the composition into the interval and solve for the new interval. But you don't retest endpoints. Here, if you differentiate or integrate, you have to retest endpoints. So that's the hard part. And let's just make sure the integration makes sense. If you integrate this, it's just a polynomial. Add 1 to the power, divide by the new power. All right. Radius of convergence is not going to change. We're still going to have this. So when it's differentiated or integrated, we have to test the endpoints individually. Very commonly, we will lose endpoint convergence when we take a derivative. Take a derivative, sometimes you lose convergence at endpoints. And sometimes when you integrate, you gain convergence. I have not seen an example where you differentiate and you gain convergence. And I have not seen where you integrate and you lose convergence. So those cases, they must happen because they're pretty particular about it, but I've never dug in to try to find an example of those edge cases. All right, so let's take a look at this. So this is the hardest type of question that's going to be on exam 3. So we've got the geometric series right here. We know the power series for the geometric series. Now we want a power series for g. And we look at the function g, and we have to come up with a template to get to g from f. So the answer is, one of the steps to the answer is, do we differentiate f or do we integrate f to get to g? We are going to differentiate because what we've seen is if you differentiate like 1 over x, you end up with negative 1 over x squared. And if you differentiate it again, you'd end up with 1 over x cubed. So the denominator here, when you differentiate, is going to bump up. Let's test it. So if we take f of x equals, let's write it as 1 minus x to the negative 1. It's easier to differentiate when you write it in that form. So f prime will be negative 1 minus x to the negative 2 multiplied by negative 1, so that will make this positive. Chain rule. The derivative of the base is negative 1. Now let's differentiate again. Bring down the negative 2, subtract 1 from the exponent, and then chain rule, multiply by the derivative of the inside. Derivatives of the inside is negative 1, so we end up with that. So this is equal to 2 divided by 1 minus x cubed. So how do we get to g from f double prime? G will equal f double prime divided by 2. If we take f double prime and we divide out the 2, don't we get exactly g? Everyone agree with that? All right, so what we need to do, so this is our template now. Find f, derivative, divide by 2. That's what we're going to do. So we did it with the function. Now we have to do it with the power series. We have to do derivative, divide by 2. So let's come over here. So the power series, we've got this power series right here. We're going to have to differentiate it twice and then divide by 2. So let's write it this way. We're going to say g of x is going to be 1/2 multiplied by the second derivative of this power series. Second derivative of that power series. Okay? So we're going to have 1/2 multiplied by, let's first take one derivative of the power series. So the first derivative, k comes down, we subtract 1. And we're going to have one more derivative to go. So let's think about the starting value of k. So when you differentiate a polynomial, you still get a polynomial, but a lot of times you lose a term. We agree with that? If you have the polynomial 1 plus x squared, if you have 1 plus x squared, and you differentiate it, you get 1 plus 2x. So you lost a term. So it's very common when you're dealing with derivatives of power series that you have to adjust the index start value. Once again, remember that a polynomial always has non-negative exponents. If you plug in 0 as your start value right here, you get x to the -1, no good. So we need to start at start at k equals 1. If we plug in 1, we get x to the 1 minus 1, which is x to the 0, which is the constant term. No problem. And so we're going to see this pattern. When we differentiate, we have to change our start value down here. Okay. Now, let's differentiate again. So when we differentiate again, still going to go to infinity. K might start at a different value. Let's check. So we're going to bring the power down. So now we bring down the k minus 1. And we have x to the k minus 2. Once again, if we think about starting at 1, 1's not a good start value because it causes a -1 exponent. That's not a polynomial. So this k has to start at 2. So now we have what we were looking for. Bless you. Now we have, this is our power series for G. From the power series for F. We differentiated twice. Unfortunately, we don't know the IOC yet. We know the goalposts. We know the left endpoint and the right endpoint. So if we come down here, we can write that our interval of convergence is -1 to 1. We know the radius is 1, but we don't know if we have convergence or divergence at those two endpoints. So we have to test them. So we have to come to this power series and now test. Let's use purple for test. So now we have to test x equals -1. So we're down here, this power series right here. We don't care what it converges to. Does the half matter? No, that's not going to affect convergence or divergence, so we can just ignore that. What we have, and we can ignore the indices, they don't matter. So we have k multiplied by k minus 1. If you plug in -1 here, we get -1 to the k minus 2. So the first question I have, this format right here, -1 to the k minus 2, it looks like a switch. We've seen in the past that sometimes things look like switches that aren't, like maybe they're always 1 or always -1. Let's ask ourselves, is this a switch? As k increases progressively by 1, do the signs alternate, negative, positive, or vice versa? So if we plug in k equals, say, 2, we get 0, so that's +1. If we let k be 3, we have a 1 here, so then it's -1. If we let k be 4. So this is really a switch. That is definitely a switch. So what kind of series is this? Alternating series. Alternating series. With an alternating series, the a sub k does not include the switch. what is the limit of a sub k here? Infinity. So it's not 0. So this will diverge by the divergence test, because the limit of a sub k is not 0. Right? The limit of a sub k has to be 0. So this diverges by divergence test. Now you don't have to write all this. You don't have to write this part down. So the limit of a sub k is infinity. It's not 0. Okay, so we have divergence. So that tells us down here, -1, we have divergence, so we're going to have a parenthesis there. And the rule of thumb that I gave you would tell us that we're probably going to get divergence at both endpoints. That generally, in order to gain convergence, it's usually done with integration. But we have to test it. So isn't that the series when we plug in 1? If we plug in 1, 1 to the k minus 2 is just 1. 1 to the power is 1. And this series is not an alternating series, but isn't the conclusion the same as that one up there? Here, your a sub k is this whole thing right there. And what's the limit of a sub k?
Infinity.
Yeah, so it's the same as that. So it's the same as above. Same exact logic. Divergence test tells you that you have divergence. So it diverges by divergence test. All right, so that is the most complicated problem that you're going to see in this chapter, where we build a new power series by differentiating or integrating a known power series. That we'll be able to get through this one, but let's at least set up our template. So first off, this function over here, f, I claim you already know the power series for it. It's just a modified geometric series. Do you agree? So we have our geometric series 1 over 1 minus x. What did we replace x with to get down to here? Replace x with negative x squared. And then multiply by x. Yeah. So we're going to take that function. So if we have the power series for this function f up here, we can replace the x with negative x squared. We can multiply by x, and we'll have the power series for f. So we'll do that part on Thursday. But let's see if we can figure out what our template's going to be. How do we get to g from f? Integrate or differentiate? Integrate. All right, let's see what happens. So if we integrate f of x with respect to x, we're integrating that. And we're almost in what form? Log form. We're almost there. We can put a 2 here. We can be creative. Put a 2 there, which means we have to put a 1/2 out in front. So this is going to be 1/2 natural log. We don't need absolute values around this 1 plus x squared because everything is positive, plus a constant of integration. So, just like up here, this is our template. We said that g of x is going to be f double prime divided by 2. So now we want to do the similar type of thing here. So our template, this tells us that g of x is going to be the integral of f of x multiplied by, if we multiply this by 2, that will give us g of x. So we're going to do 2 multiplied by the integral of f of x dx. And yes, there's a constant. We'll deal with the constant thing on Thursday. we'll see what happens. But if we multiply this by 2, we're going to have g. And yes, there's going to be a constant here, but we'll talk about the constant on Thursday. We'll see that constant's probably 0. We'll see. We'll talk about it Thursday. All right, let's stop there. We've done enough math for now.
This does not bode well for the grade.
Does not bode well for what?
The grade book.
It does not bode well for the grade.
Thinking about our wizard movie.
Ugh. All right. Anyone have questions?